on the Government Advances in Statistical Programming Conference, and welcome to day 2. This is our schedule for the day. We have 3 paper sessions and a couple of lightning talk sessions, so it's a real jam-packed day. If you want to get a copy of a detailed program that has abstracts in it for each of the talks, you can do it by scanning that QR code. And then a little later, I'll go ahead and start putting links in the chat so that you can get hold of it that way as well. Quick reminder about the rules of the road. Some of you may not have been here yesterday when we talked about this. The attendees are all going to be muted. If you want to ask a question, you're going to need to use the Q&A feature at the bottom of your screen to do so. The useful thing there is that then the speakers can also answer the questions within that feature. And if we have time, then we can ask them to sort of verbalize that at the end of the session. The chat, there's going to be additional information that we'll put in the chat. Like I said, the link to the full program with the abstracts will be put in there. Any other kind of useful stuff that folks want to put there. The panelists, so the presenters will have a chance to put things into the chat as well, but attendees won't be able to post there. If you need to, you can turn on closed captioning for this webinar. And then our time zone, if we failed to put that someplace, we're on Eastern Daylight Savings Time, UTC -5. The sessions, generally, each of the session chairs will run each session, to their, as they see fit. Papers are generally going to have 12 to 15 minutes, and then the lightning talks will usually have 6 or 7 minutes, and then the session chairs will moderate the Q&A. If you have any problems, contact both Peter and me via email, and we'll see if we can get that fixed for you. So without further ado, I will go ahead and pass the baton to Matt Williams from RTI to chair the first session. Thank you all very much.
Thanks, Lisa. And so it is a jam-packed schedule, so I won't use up too much time. This is the session on small area estimation. Our first speaker will be Jingyu Zhang. We'll give you all about 13 minutes, and when that happens, I'm going to jump in and ask you to wrap it up. So, Jingyu, can you share your screen?
Okay, so can you
all
see?
right, I can see it.
Can you see?
Just get full screen for us. All right, thank you.
Okay. Okay, happy Wednesday, everyone. So my name is Xinyu from Bureau of Labor Statistics. Today, I would like to share some work on small area estimation. At BS, we more often call small domain estimation. So we put a nice team together: Danny, Mark Hudak, Mark Notal, Irene, Kelly, Richard, and Cosmo. What I will present is just authors, doesn't reflect the view and policy of BS or Department of Labor. I'll give you a brief background about odds and also small domain estimation with odds and the general procedure, but we'll focus on the multiple imputation variance estimator for small domain variance estimation, because we have to address uncertainty from the original odds and the model prediction itself, and also because we're using large sample, exception sample, operational employment and wage statistics for prediction, which is a survey program produce operation specific estimates about the employment and the wage. Small domain or small area is defined as any estimation domain where directed survey estimates don't have enough adequate precision because of small sample, or not available at all because of no sample. Usually called the geographic area. That's why we call it small area, more for population and household survey, population groups, industry sector, and the occupation groups. This is our case. There are two general modern approach. One is area model, which is more the aggregate outcome of the domain of interest. That's really more common. but also there's called the unit level approach, which will predict the value at the unit, sample unit or population unit in the frame, and then aggregate for small domain estimates. All is survey conducted by BS to connect data, measure the job requirements in the U.S. economy in 4 major areas: physical demands, environmental condition, education, training, and experience, and also mental and cognitive demands. The sample design is a two-stage stratified sample design. So we select the establishment first, then select the job quotas within the sample establishment. The strata formulation involved ownership, geography, industry, and the occupation. That's also the information we seriously considered in our model specification. The total sample size is 60,000 for us between for 2018 to 2023. So 85% are private industry establishments, and 15% are state and the local government establishments. The objective of small domain estimation is to produce reliable estimates for all 844 targeted occupations, which is we call represented with 6-digit sort. And for the odds 2018 to 23, we total connected 112,146 job quota with valid data from 830 sources. So that means we have 14 sources without a sample, without a usable data at all. Among those sources with data, the median job quota sample size is 43. On average, it's 135. It's nice, but we still have 329 sources with less than 30 job quotas, which means we don't have. It's really challenging to have reliable or valid, even important unbiased estimates. And we take a multi-level regulation and a post-stratification approach for small domain estimation. So we also often call it LIST-P. So because the basic idea is we're using survey construct multi-level regression model. On the generalized linear model, we have both fixed fit, random fit, and using the fitting model to impute the sample unit or population unit. Here, we're using large sample or AWS, then aggregate by domain. We impute individual unit level value, we easily aggregate the by domain, get the estimate we lack. But during this process, we have to obtain the appropriate variance and the reliability measure we made best, variance or standard error. So we propose the multiple imputation variance estimator in this study. So again, the first step fitting the model, we have the value outcome and also the fixed effect included is establishment ownership, employment sites, geography, and the industry group. And the random effect is the occupation specific random effect. So this process is basically a statistical learning process from the entire odd sample survey. And with after fitting the model, we could that's good things of model. We could produce any possible combination with the NAC, And totally, since all predicted a category, we could predict the possible value is almost 5 million. And then we predict for those OEWS job quotas, which is 10 million cover 80 million jobs. So the job sample rate for OEWS is more than 60%. So that's why, with the individual predicted value, with all AWS weights and the number of jobs for each job quotas, we could easily get the estimate for the domain of interest. In our case, is by source. Small domain is essentially a massive, data imputation process. So that's why we consider the multiple imputation perspective for variance estimation that account for the uncertainty from odds and model prediction and OEWS. And for odds, we try to using the full sample and 80 requests to fit in the part of fitting the model, make predictions. And then through the parametric bootstrapping, we try to incorporate the uncertainty with model prediction. And we include the finite population correction factor in the variance estimator and to take care of the OEW sample design effect, include the weights in part of the estimation. The good things we have really nice, well-known total variance, right? So given the predicted or imputed value, we could get the estimates, right? That's the first part is more social. For us, is we're using the BR balance repeated replication method balance estimator. So that's part associated sampling, and the second part is the parametric bootstrapping between associated with imputation, and with in our case it's parametric bootstrapping. So together, the total variance here, the specifically how they are feeding into this variance estimator. So you see, we do at first we do using the predicted value for OEWS unit and predicted value feeding to the BRR variance estimator, and we also adjust the OEWS finite population correction factor, and the second part is associated with imputation. So we have the variance component based on all the sample from what's sampling from all, right? So that's based on the PR variance estimator that is expected to mean. But we do, take care of the OEWS high sampling rate, global sampling rate. So together we get the adjusted, variance sampling. Both basically cover associated with sampling. The other part is imputation. Here we added the one, Rubin's rule, added the one divided by n. That's the number of imputation. In our case, it's number of bootstrapping samples. So we reflect the age probability from finite number of imputation rather than infinite number of imputation. And together, we get the total variance. And of course, we're interested to see which one is more dominant, especially at the US level, but also at the occupation level. We consider two comparison metrics. One's estimation error, which defines the difference between model-based estimates and the reliable derived sub-estimates. And the other is coverage accuracy, defined as if if the model-based estimates are within the 95 confidence interval of derived sub-estimates. At the US level, first we try do the parametric bootstrapping, because usually people say it's around 20. That's a recommendation, but we tried 20 to 250. It looks like the number of imputation or bootstrapping, 20 or versus more, produce similar point estimates and also variance estimates. So that's why we could go with 20 for all the rest of the work, because anyway, it's time consuming process. You go to 200 every time. And the other is variance from sampling at the US level is dominant compared variance from model-based estimates. From model-based imputation or prediction. As we mentioned, the challenge is, the job requirements go to many multiple categories. So like SVP is a 9 category. So as you can see at the US level, the bias is very limited, and the model-based estimates definitely have relatively smaller, more reliable than derivative, but both are quite consistent. And for extremely low one, we'll still also be able to produce equivalent estimates. So basically, we go with the simple logistic rather than ordinal, more complex ordinal multinomial, because ordinal, the strong assumption of proportion odds ratio. Multinomial is too logistic model is too demanding. It's so much in such a complex mixed model. So looks our estimator works well for multiple category outcomes and even for extreme rare categories. How about the occupational? So for large sample size, occupation A with a pretty large sample size, more than 2,000, they produce very consistent model-based estimates, and the variances are very consistent with the derived sub-estimates. So that's expected. And even you see some accuracy is 0, but if you look at the bias, look at the actual number, I'm confident that economically they are equivalent. How about the median sample size? So as you can see, there are some reliability, for those non-reliable estimates, it's harder to, the bias is large, but model-based estimates, they are compared to the relatively reliable, more reliable than universal estimates. But for those non-reliable, we still don't know if the universal is biased or not, right? And so that's the question, how do we know, the model-based, is accurate, as expected. And if you go to the smaller one, as you can see, server-based estimates is not reliable at all. And so we do have reliable model-based estimates, but the point estimates and the reliability, especially point estimates, we still are not sure they're valid or not, right? That's the challenge. And remember, we still have occupation without sample more. Then you could see those, even model-based here, we already try to borrow information from the adjacent occupation and get it. We still have not, a variance and the standard error. So that's the challenge, We could produce model-based estimates, but how about to validate them? So that's why we propose two approach, for those occupation, because for large one for occupation with large sample size, that comparison is consistent but doesn't confirm those small one or without the sample. So for those small one, we drop the occupation with large sample size, then compare model-based estimate with the sample estimates, right? They're out of equation, then you see how accurate they are. The other is reduce occupation with large sample size, then to smaller one, like 5, 15, or 30, then compare model-based with the sample estimates. Of course, ideally, we want to have good external data to validation, but usually this is not available. That's why we consider this innovative approach to for validation for small and for operation with small sample or without a sample at all. This work is still going on. Thank you. Any questions?
Awesome, thanks. Perfect timing. If we have questions, we can put them in the Q&A. We'll transition to our next speaker, Stas Kalinikov from NORC.
Okay, can you hear me?
Yes, we can hear you.
Mm-hmm. Awesome. Sure. You should be seeing my title screen.
Yep, got it.
Right. Okay, awesome. So this presentation is only touching small areas. So this is more on statistical programming. So I'm a real data scientist in the sense that I know more about programming than typical statistician. I know more about statistics than a typical computer science. I am in this capacity. I am working as a statistician for an academic client. I am not going to mention what that thing is, other than this is public health domain. This disclaimers apply here. I've consulted with Census Bureau. That I'm not talking too much about any secret sauce that the FSRDC is. So FSRDC stands for the Federal Statistical Research Data Center System. We are working within the FSRDC primarily because we need to produce small area estimates using the restricted geographic data, and the health behaviors on the study are quite sensitive as well. So FSRDC system is a system of centers that are scattered across research universities and Federal Reserve banks. And the one that I have is a 15-minute commute by bike for me. Some other people like Claire Bowen, who talks about privacy and disclosure, says that her nearest RDC is 8 hours away on an 8-hour drive somewhere else. So I'm lucky to have one by my side. There's a variety of federal data sources available in the RDCs. I went through the clearance process to receive the special sworn status, and I have a badge that I need to swipe to get inside. So there's several layers of protection in there. So I have some guesses as to how many compute nodes they have and how big they are, how much RAM they have, how many processors, but I'm not gonna delve into that. So this is a research environment that's shared between several hundred, I think, census economists and another several hundred academic researchers like myself who work on the restricted data. The usual suspects of SAS data and R are there. You need to provide this there's a, as far as R goes, there's the internal mirror of CRAN that is that I can install packages from. No, let me take this back. They don't have the CRAN mirror. There is some limited set of packages that are pre-installed, and for other packages, I need to write specific requests to get them there. One big limitation of FSRDC system is that you don't have access to the internet at large. If I need to get something off the internet, I need to step out, take out my phone, look at something on my phone or on a laptop, and bait myself in trying to hold this in my brain. Not the most productive workflow. So what I've done is I've went to the package down, book down websites of the packages that I really needed, like targets. I forked them and compiled them into PDF books, changing the YAML headers as needed. Special fun for the packages that don't really build that way. So reproducible workflows. This is a sizable project, right? So I have few dozen substate areas that I need estimates for. I have well over 100 health outcomes when they are detailized because they're broken down by age as well. So there's a lot going on, and working on a project of such scale requires attention to computational details. So and what is happening here is I need to check, okay, well, am I using the right data set? Have I recoded those variables correctly for my use, blah, blah, blah. Am I using the right version of the code? So if I reran my direct estimates, what do I need to rerun later for the Fay-Harriot component of the code and whatnot? So all of that kind of integrates together with the reproducible workflows system. So I'm giving references here to Lars Wilhuber's tutorial. So Lars is the American Economic Association chief data officer or something like that. Not exactly. This is the he's the leading the reproduction of the published results across American Economic Association journals. So he said, I think he mentioned once that he is overseeing about 2,000 reproduction efforts per year across the various publications, and this tutorial is specifically aimed at the FSRDC users in terms of establishing those workflows. So this is kind of shut out from the past, and I don't know if I can really switch there. This is from several years ago, and Jenny said, if you set WD C users, blah, 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 she'll come and set your computer on fire. And if you RAM list ls, she'll set your computer on fire. And if you have not seen that post, you should really read that and see what that project-oriented workflow is. So the most recent kind of addition to this ecosphere is the book by Bruno Rodriguez, where he kind of put this all together. He teaches a semester-long course on the topic, and that's a full full-length exposition. So there is a minimal Git environment provided within this FSRDC. So there's a command line Git. It's just not the greatest thing to use. I end up using RStudio built-in client. And I believe there was a Git training at the GASP workshop last year. So this is the basically the system of tracking changes in your text files line by line, figuring out who contributed what at what time and for what purpose. Originally, this was designed to build Linux kernel, and we are using this for everyday code. I have the habit of basically slicing this down to maybe like 20 lines of code is worth one commit. Other people have the workflow. I work for the whole day. I'll commit the end of the day. And that's a style issue. I think I'd like to see a more detailed functionality of that, and don't commit to the master branch. But I'm doing that as the only person working on this project, and kind of excusing myself from this abominable behavior. So another part of reproducibility is how you set up your things up in terms of directory structure and whatnot. This is, in this particular case, it's dictated by FSRDC rules that this is where the data is supposed to sit, this is where the code is supposed to sit, and I'm limited by that. I'll return to this point a little later when I talk about our projects that I'm working with. One thing I advocate for internally within the company, I want to advocate for this workflow here at this conference is packaging, developing our package for every project that you're working on. So, and there are a couple of papers where that go into full explanation of that. One is the American Statistician, another Behavioral Research Methods. Sharing and organizing your research products as R packages. And this one is not gonna go up. Basically, you put your scripts and your functions into R folder. You put your data into data folder. You provide your explanations in the vignettes folder, and you free write the infrastructure of our packaging in terms of having tools specifically designed for package development to simplify your tasks. It is becoming especially more important, as I hope my next slide is on targets. It's in a couple of slides. So basically, my internal package would have something like process survey data into interim data, produce direct estimates, fold in SAE covariates, run lasso selection, run for Harriet machinery. This is very simplified kind of presentation. There is a lot going on, a lot more going on in there, and produce output, which is the table shells that were approved by the RDC, and produce cell counts for the disclosure review. Again, this is a requirement internal to the RDC specifically. So all of my 100 plus outcomes are processed using some sort of attributes defined inside are attached to my outcomes. Those attributes say, well, this is a continuous outcome versus binary outcome. This is the outcome that goes into Excel tab, this Excel tab and this in this position. So rather than writing output as some sort of concatenated data table, I found that this is, again, given that the table shells have been approved and they have already structured, that makes more sense. So what the packaging workflow is especially useful for is tying this up with the targets pipeline. So again, this is something that I advocate for every project that has more than 3 data files. Once you have some sort of arrows going, if you have a project structure like this, with this your input and output files, this is a targets diagram, some sort of interim targets diagram. This is why you need this. You won't be able to keep track of what's outdated, what needs to be rerun, what the dependencies are. So I imagine that something like this is probably an interim data set that's being used by all those outputs that are various regression tables or other output tables. And there's some preparation happening here. This is not my pipeline. I just stole it somewhere on the internet. So if you're familiar with Make, if you're a computer scientist, then you've seen Make, and this is basically in our native implementation of Make. It has some dark magic of figuring out what the dependencies are and parsing them. And this is how this targets pipeline looks like. You're saying, well, this is my first target is the input file. I do some work on it using get data function. I process this into the work file with recoded variables. I feed my models. I export the substantive results to one file. I export cell counts to another file. In reality, there's more. I ended up with about, I think it's more than 2,000 targets. I think it's more like 1,800 targets.
Hey, Still, it's about a minute to wrap up.
Yep. Okay. So as I said, targets and packaging kind of reinforce one another. And my packaging, my project structure is I have 2 separate R projects. One is code development that gets where I install stuff, and another is the targets pipeline with I don't touch very often. And I may be the only person mentioning Stata at this conference. There are some alternatives, kind of similar Make capabilities. And I have a training on that project command as well. And that is actually all that I have. Thank you.
Awesome. Thank you. Perfect timing. Just a reminder to anyone join, there's a Q&A feature, so you can post that and the speakers here can respond offline. So I'm going to turn it over to our last speaker, Joseph Kang. Take it away.
Hi. So Adam and I will present. Adam will go first for the first half. So Adam, you can go first.
Okay. Just checking. Can everybody hear me?
Yes. And can we get those
Perfect.
slides full screen, please?
Okay. Hold on. Let me see. How do I do full screen?
This slideshow, I think.
Okay.
This works. Okay. So hi, everybody. I'm Adam Hall. I'm presenting this with my colleague, Joseph Kang. And go to the next slide. So this project is specifically in service of Section 203 of the Voting Rights Act. What is that? It's basically a law that says that some places have to provide non-English voting materials, instructions, ballots, other kinds of things like that, so that people who don't speak English well can still participate in the electoral process in the United States. So the question arises of where this has to be done. There are certain places that are called covered jurisdictions, and the decision about which places are covered jurisdictions is specified in the law to depend on certain kinds of quantities that we want to estimate from American Community Survey or decennial census data. And so the main point of this small area estimation project is to try and get those quantities. I won't go into a huge amount of detail as to the exact algorithm by which this is determined. That's available to look up online, but it's enough to note that there are a few kinds of quantities that we need to estimate with our models in order to make those determinations. So you could go to the next slide. So in general, we need to know for each language minority group, the number of voting aged persons, the number of those voting aged persons who are citizens, the number of those voting aged citizens with limited English proficiency, and the number of the ones who have limited English proficiency who are illiterate. And this is in each jurisdiction and language minority group. We're going to take sort of a similar approach to estimating each of these different quantities. So for our paper and also in this presentation, we're going to zero in on limited English proficiency over voting aged persons. And you can see that there's kind of a nested nature to these data. They look kind of like this target where voting age persons is a larger set than voting age citizens, which is a larger set than limited English proficient voting age citizens, etc., until you get to voting age citizens with limited English proficiency who are illiterate as the smallest sort of the groups. So next slide. So in the past, this was done initially using direct survey estimates based on sort of the long form census, which became the American Community Survey over time. But a problem with doing it this way is that many of these combinations of language group and jurisdiction have very small sample sizes. You know, you have a whole bunch of different counties. A county is an example of what might be a jurisdiction. And you ask, you know, for a random county that might be very small, how many, say, Korean speakers are there who are illiterate in this particular county? The answer might be a small number, and it might be that there's a small sample size in the ACS sample of people who match that sort of criteria. So you get a lot of noisy, unreliable estimates. So since 2011 or so, small area estimation models have sort of stepped in to try and improve these estimates over time. And since that began being used, the models have grown more complex over time. So more recently, sort of in 2021, there was a combination of a bunch of different models that were used depending on the size of the sample and what that would support in each of the different domains that would be estimated. So there was a Bayesian model called multinomial logit normal full. There was a sort of cut down version of that called multinomial logit diagonal, which had a diagonal covariance matrix assumption. There were beta binomial models. There were other things too. And there was like a system of rules to sort of switch between these things. It was a little complicated. Major limitations of this were there was manual variable selection. So the variables were selected based on some of the larger groups, and that set of variables was applied to predict everything. It assumes, as most sort of linear models do, a linear relationship between the covariates and the outcomes, and there were no interactions among the covariates included in the model. And these assumptions, if they're not true, which they're probably not true, could lead to some sort of biased estimation. So to address these, we're experimenting with using machine learning methods, in particular random forests in this case, to try and get these quantities that we want. So a machine learning method, it generates many sort of decision trees based on multiple bootstrap samples based on the original data, and then aggregates the results to form a prediction. Now, an advantage of this is the sort of covariates that are used in each of the different trees are selected sort of randomly in terms of how the trees are constructed. And so in some sense, variable selection is sort of automatically addressed. And it doesn't assume any kind of linear relationship between the covariates and outcomes. for that reason also, it can find complex interactions among features, so it doesn't have to assume a null interaction term for the effects. So I'm not going to give an entire introduction to random forests, but just generally, you have a whole bunch of what are called decision trees. The decision tree basically asks a question of the data, like, is the proportion of foreign-born citizens high or low according to some definition of high or low? That definition of high or low is decided upon by some value of that covariate that is determined based on what gives sort of the best or optimal result. And the tree splits the data into groups based onto the answers of that question, and then it asks another question about a different covariate. And the split points in this case are chosen specifically by maximizing the probability of accurately estimating in each of the splits of the tree. And if you grow each tree out to a few different branches and then you aggregate over all of the different trees, the model can become robust and accurate in terms of its predictions. So in terms of the data that are used for this, we use 30 covariates taken from the 2015 to 2019 5-year American Community Survey. I'm not going to say them all because we'd be here all day, but you could have, for instance, a proportion of citizens among voting-aged persons, a proportion of non-Hispanic white people, college education variables, things like that that seem like they might plausibly be related to English speaking among these different immigrant or foreign language group populations. So sort of a nutshell of how this works is for maybe 100 times, you could draw a bootstrap sample of the counties, grow a decision tree from that bootstrap sample by picking some number, say 8 covariates at random from those covariates. For each of those, growing a tree by finding the best variable and split points. And then you get sort of predictions based on the terminal nodes of the tree. And you can aggregate the ensemble of those trees in order to get the prediction. So brief preview of sort of the results before my colleague, Dr. Kang, goes into more detail about how the model works, is that the random forest model seems to outperform the previous 2021 model fairly significantly. It does much better in smaller counties and similarly to the previous results in larger counties. And this is pretty significant also because there are more counties with sort of small sample sizes than there are with really large sample sizes. And counties with really large sample sizes, direct estimates may be more useful in them. So this is really where we want to improve a lot.
Okay, I can take over from here. So what Adam explained was model diagnostic table. So in this case, jurisdictions were gathered into one bin, meaning just one person to 4 people in one sample bin. In this case, standardized delta value, which is like a discrepancy between model and also data direct estimate. So you can treat this as like a, standardized normal random variable, hoping to see less than 1.96. The previous one, STD or model is 3.2. The random forest gave 0.7. This was meaningful because in the smallest areas, we have more accuracy in random forest prediction. Okay, so I think we just mentioned this, and so briefly touching random forest again, bootstrap method. I think this can be important for all practitioners using small area as a sampling unit. So let me be very clear. Random forest trees are built using bootstrap samples. What are bootstrap samples? They are creating random subsamples, right? Randomly, drawn with replacement, with an equal chance of being selected. This is important. It is well known that if data are imbalanced, the bootstrap method does not work well. It is noted in earlier development. When random forest was born, it was already noted there. So by birth, I mean, in the time of birth. Because of disclosure avoidance, I couldn't show the plot. So let me draw the picture for you. So suppose we have a language minority group, which is rice cubed. So like going like this and going down, okay? And then x-axis like basically jurisdictions. And each jurisdiction has a sample size 1 or 2 people, voting age people. So majority is centered at 1 or 2, okay? And then this is like 5 or 4. And so let's say there are like a 400, so one jurisdiction has a 400. What random forest does is that it resample this jurisdiction with replacement with equal chance. So as a consequence, you ended up drawing a lot here. Oh, that's fine. That's fair. You can draw. So this is distribution. However, there's a random chance that you omit one large jurisdiction, like at the tail part. Does it have a consequence? Yes, it does. So for example, like as I showed you, we have 6 different sample size bins. So jurisdictions were gathered through 1 through 4, 5 through 12, 13 through 25. These are like, voting age persons in jurisdictions. So jurisdictions gathered. Why are we doing that? Because when we gather this many jurisdictions, the large sample theory tells that whether direct estimate or model-based estimate, they should be equivalent. And the standardized delta value should show that the value should be less than 1.96. But you look at this. When you see sample size being over 200 voting persons, then you see like an extreme imbalance. Again, this value should be less than 1.96, but it ended up being huge value. Okay, so this is another like a red flag. We get it. Now, using some method, this imbalanced data turned out to be like way better. It's close to 0. How? So this is a major point that I want to emphasize. When we build random forest model for or any like jurisdictions imbalanced area, you will face this problem. Why? As I explained to you. So omitting extreme small like one jurisdiction randomly and can cause this bias, prediction bias, precisely. So the method that we were thinking is amplification. So the concept is that suppose we have one jurisdiction, which is about sample size 400 voting age people there. And we can conceptually divide 400 into 8 sub-jurisdictions. Why? So that we can increase, selecting these jurisdictions. We will not miss. That's it. That's the main idea. Okay, so again, there's one jurisdiction that has a huge 400 people, but then we divide this into conceptual sub jurisdictions. Mathematical justification. If you review Bootstrap, what is a Bootstrap? Suppose there's a random variable x.
So we need to wrap it up in about a minute, okay, Joseph?
Okay, sure.
Thanks.
So I don't think I should go through all the details. Long story short, there's a Bootstrap sample without amplification. We introduce a amplification constant C, which is 8, conceptually divide, and then you add additional weight. All this like equivalent. In theory, equivalent, but when we introduce amplification concept, we were able to reduce the bias. Extreme value we detected through this diagnostic table, and the way how we chose is that second largest sample size being 50 was chosen so that roughly 400 divided by 50, which is 8, And that's how we got the 8 number summary. So we introduced random forest method to adjust number of voting age persons in jurisdictions. And then we also introduced concept of amplification so that we may, reduce or attenuate prediction bias. Okay, so I think that's all I can present.
Awesome. Thank you so much. Thanks to our 3 speakers, we have about 5 minutes for questions. I see that there's one in the Q&A. I don't know if y'all can see that one. I think it might be for the last session, but if any of the speakers have questions for each other or any of the attendees have any more questions, please put that in the Q&A.
I think I can answer the question about ban. So the question was, can you share a little bit about how standard errors or confidence interval would be produced under the this area, maybe through conformal inference? Well, this is like a really primitive way. We use a replicate weight. So in other words, we have 80 replicates weight, 80 different weights, and then we fit random forest 80 times. I know it sounds like not recommendable, but we try to make more fancier variance estimation using one random forest. So we use like a replicate weights.
Okay. In the Q&A, I see a question from Baiwan. For the policy, is the desired estimate and point estimate or probability of at least X number or share of eligible citizens within scope? Do y'all see that?
I'm sorry. So Jose's question is for our session.
I believe so.
Okay, so is the desired estimate the point estimate or the probability? Oh, okay. So initially probability. So for example, like how many, what is the proportion of like, US citizen with limited English proficiency. So once we get the proportion and then we multiply it by total voting population for jurisdiction. And that's how we get, the sub numbers. Yeah.
Excellent. Well, thank you again to all our speakers. We've got a minute or two to transition to the next session, but I'll remind folks that you can use the Q&A feature and we'll be monitoring that. And so we can try to answer that offline.